alpha 1, alpha r, x1, xs. So these are in the dual, right? And these are in V. So the definition here is just, what's the isomorphism? The isomorphism is simply the following. These are in the dual space, right? I'm assuming that. So alpha 1 can do what? Alpha 1 can act on EI1. This makes sense because I have a covector operating on a vector. That gives me a number. And likewise, take the product all the way out to alpha r acting on EIR. And then let's see here. And then for the rest of it, I've got like EJ1 acting on X1, EJS acting on XS. So that makes this mapping, and then you extend linearly. That makes psi a mapping from the formal tensors to the multilinear maps. You can verify, in fact, that this is an isomorphism. So the way I usually teach this course is to not even talk about tensors formally. My typical starting point in here is I just say a tensor is a multilinear map. And we go from there. And I just talk about bilinears and trilinears to start with. And that's probably a better way to teach it. But I wanted to take Rentlin out for a spin and see how it felt. It feels confusing for this class. I don't know. Maybe it's not confusing, but oh, good. I still got time. So again, the difference in the question is, do you want to think about the tensor as just this abstract algebraic object, right? Which is what I started with. These don't do anything. I mean, are these active objects? Are they acting on anything? I mean, no, it's a vector space and complex numbers. They're just sitting there. We study them, right? We don't think about them being functions of other things. In contrast, multilinear maps, they're active objects, right? I mean, you think about what do they take in and spit out. See the difference in viewpoint? Right here, I can take any one of these formal objects and I can convert it to a multilinear map in exactly this way. And then I extend linearly. Let me be more specific, more explicit. All right, so back to basics, if you don't mind. If I have B, I'm mapping from, say, V cross V into the reals, right? Then this is said to be bilinear when what? We have what? We have B of Cx plus y comma z. We've seen this in the homework before, right? And I think I've talked about this in class, yeah? In the test, yeah. Good point. Oops. Like that. So what I'm telling you now is that B is a type what? Yeah, type 02 tensor. on V. I am now going to make the identification that tensors are multilinear maps. Okay? So I'm replacing that formal idea with the concrete realization that we can build these up. And you can check that multilinear maps do in fact have those distributive and associative properties that I was bragging about at the start for tensors. Right? So I mean you can check that those are actually, that's actually true here. Now, just a little bit more on this one. So just what does a tensor look like? Well, if we look at B acting on x comma y, well, let's look at the basis, right? This is B acting on what? Sum over I of x upper I, e lower I, right? Sum over j of y upper j, e lower j, right? And so how's that go? Well, you gotta pull both sums out. And we get what? And pull the constants out too, right? X sub I, y upper j, and then we got b, ei, comma, ej. And so the typical notation is that this is the b sub ij. These are the components of the tensor B with respect to the basis. Let's say the beta basis. So we're working with today. Well, and we can do a little bit more than this, right? We can, yeah, right. Well, let me just rewrite this just a tad here. We can also rewrite this as ij, b, ij, e upper I, tensor e upper j, acting on x comma y. Now there I'm assuming something I haven't shown yet today, all right? Now to get from here to here, I need a few items. And they're probably logically included in the isomorphism I wrote over there, but goodness gracious, let me be a little bit more explicit and down to earth. Exactly. So, I mean, that's a good question, and that's a good comment. So, we had EI, EJ was equal to Kronecker delta IJ, right? So what happens when you have EI acting on a vector x? Well, that's EI acting on some j, x upper j, e lower j, right? And so that is sum over j of x upper j, e, I, e, j, right? But this is Kronecker delta ij, which is what? So this whole sum collapses down to just I. This is a fundamental lemma that we should remember, which is that the dual basis acting on the vector simply picks off the ith component with respect to that basis. That's one of the reasons it's good to study dual bases. Nothing else. And likewise, E, J acting on Y gives me Yj, right? Now, here's the thing. I've just thrown this out, EI, tensor EJ. Now, I guess at this stage in the game, I really should make a definition. This acting on a vector x comma y is definition what? See, I've done a change of viewpoint here. To start with, we were talking about tensors formally, right? Now I'm talking about tensors as multilinear map. So I'm obligated to explain to you what do I mean by the particular multilinear map EI tensor EJ. That's a multilinear map of type 0, 2, because it's a covector tensor, a covector. It should eat a pair of vectors. What's the definition? The definition is very simple. It's just EI acting on X, EJ acting on Y. But that's what? Right? So you go back over here, and now you can understand what I did right here. See what I did? Was I took this thing right here, right? And I rewrote it as this acting on that. And then I took, and I used the sum of linear maps, and I rewrote it as just one function acting on that xy. I mean, technically speaking, it's Bij, it's like B11 E1 tensor E1 acting on xy, plus B12 E1 tensor E2 acting on xy, added together, but the sum of the functions, using the pointwise addition of functions, I can group it all into one big function acting on the pair. What does this show? The tensors of type 2, 0, no, other way around, right? Yeah, 0, 2. 0, 2 over V are a span of EI tensor EJ. Is that right? Yeah. IJ equal to 1n. All right, let me tell you where we're going. Next class, I will try to be a little bit more systematic. I'll start by defining a little bit more about how we take tensor products of multilinear maps, right? Probably not too much. I think I've captured the main features today, but so next class we'll talk more about tensor products, and we'll also start talking about wedge products, right? We'll talk about how you can look at particular mappings on V cross V that are multilinear, but also in addition have either symmetry or anti-symmetry in the arguments. This leads us to the concept of alternating tensors, which then have their own special algebra, which is known as the wedge product. So we'll try to discover that, and I'll try to work more of these basic things, like how do you build the bilinear maps or trilinear maps or whatever from various spans of basis. So the basic ingredients for the moment, though, are the basis for the vector space and the basis for the dual space. Now, I should tell you, it does get more interesting. Like I'm trying to suffer through the algebra, and I don't think I'm doing a great job of it today. I'm sorry about that, but ultimately, though, we do this. All right, the EI will eventually transition to partial x upper I at P, which will be the tangent space at P to some manifold. And eventually the E upper J, let's say, will transition to dxj at some, well, we usually drop the P, but that will be an element of the dual space to the tangent space like that. And then we'll think about not just at one point, but a string of points in which we assign these things along a whole string of points. We get what's called a vector field. If we assigned these things along a string of points, we get what's called the differential form. We'll learn how to differentiate those and integrate those, and, well, these ones, and put them together with wedge products and everything. That's where we're hopefully going. But right now I'm just working on the underlying linear algebra of what a tensor is. And I'm sorry, there's not, I don't at the moment. It'd be nice if I had some kind of problem we could solve, something to motivate it, but at the moment it's just kind of a lot of definitions. So I don't know if you guys can think of a good problem that we need to solve. I'll see if I can do it.